Hello, folks. Welcome back. Welcome to our last session of today's hall two or room two. We have with us today Argo, who will tell us about something very interesting using layered models in computer vision. Everyone is so hyped about AI that I think that this topic definitely fits our interest. So, Argo, the stage is yours.
Hey everyone. So I would like to talk about a tiny little technique in computer vision, which we will discuss a couple of cases where we can use it. But let's start with some basics. So computer vision is generally speaking when we use an algorithm to analyze an image. In our case, we're going to talk about deep learning and neural nets for image processing. And classification is the simplest problem, and it's when we use a neural net to classify what is on the image. For example, is it a dog or a cat? So classification is the most basic task. We give an image to the neural net and get a class prediction. That's it. But in real world, classification is not that useful just by itself. In a lot of cases, we need an object detection or segmentation algorithm. In an object detection task, we have just two subtasks. The first one is to localize our object, and the second one is to classify it. And when we find an object, we localize it with a bounding box. It's the red thing you can see here, or it's also called a B box. Computationally speaking, object detection is a lot pricier than just classification, so we're going to keep that in mind. Now, let's get closer to real case where we can make use of an object detection algorithm for like real business problems. Imagine that we have a lot of security cameras and we want to make sure that our building is safe. Maybe it is a school or a shopping center, and we want to detect any situation where someone gets in with a gun, with a visible gun. It would be really expensive to have a lot of security guards who were watching every security camera. So it would be nice to have a neural net which can process video streams from all cameras and send an alert if anything suspicious is happening. That's an object detection task, by the way. But because the system will work 24/7, we will get false alarms. And by false alarm, I mean when the model thinks that some random object like cell phone is a handgun or something like that. And it gives a false alert. So in this kind of system, we are going to need an operator to validate our alarms. And we will talk about it a little bit later. Now, let's touch on the difficulties. There are three main difficulties in this task and a lot of other similar tasks. The first one is that our solution needs to be fast. It means that it should be able to process a lot of frames per second. And more cameras we have, more frames we need to process. Of course, we can't just use like infinite amount of hardware because if solution is too expensive, it doesn't make sense for a business. Faster neural nets we have, more frames per second we can process on one particular server. Second problem is a lot of like false alerts. We've already talked a little bit about that, but basically we need to process video streams 24/7. And that's more than 2 million frames per day per camera. That means that even if we have a really low rate of false positives, we're still going to get them, and maybe even a ton of them, just because the number of frames is so huge. And we can't afford a lot of operators to check if every alert is real, because our solution is going to be too expensive, of course. And finally, the third problem. The thing is that the first two problems don't play well with each other, unfortunately. as it's always a trade-off between accuracy and speed. So faster neural nets we have, less accuracy we get, and more false alerts we create. Usually, if we want more accurate models, we need more hardware for running bigger models at needed speeds. But what should we do? Is there anything better to deal with this trade-off? And fortunately, yes, there are like several techniques so we can deal with it. But I'm going to talk about one of them, which has shown its efficacy in different cases. The idea is to use two neural nets in cascade. It means one after another. But both nets are tuned in a specific way to complement each other. The first neural net is a fast detector, so it runs on the whole frame, but downscaled to 640 by 640, and localizes interested object and classifies it. This model should be tuned to have higher recall, sacrificing precision, which means that the model will try to always detect a gun, but of course it will often give a false positive on something like cell phone or something else. Detector should be trained on relevant to inference images with guns. The second neural net is a classifier. It runs on the crop made by a detector. So it runs only if detector finds anything in the frame. Specifically saying, we take coordinates of the crop from the detector and get the crop from the original image. So we can use higher resolution image for the classifier. Basically, classifier's task is to validate if chosen by a detector object is a gun or not. Classifier should be trained on the crops from the detector, obviously, but it should have several classes, not only a gun, but some other objects which are often detected as a gun. For example, cell phone, umbrella, and some other things. And why does it work? Why does this technique performs well? Let's firstly discuss why it is fast. Basically, the speed of our solution is tied to the speed of the first neural network, the detector. It's because our second net runs just in cases where the first net finds anything. So, in our case, in 99% of the time, our second neural net is idle. And the second thing is that because we have our classifier, we can pick something like a fast detector. We don't need it to be really accurate. We want it to be fast and to find like every situation where there is a gun. So these 2 points are really good for our speed. And now let's discuss why we gain accuracy. The first thing is that we use an ensemble of two models. We use different data sets for our models, and our classifier is tuned to distinguish guns and other similar objects. Next, second model gets full resolution part of the image. As I've told before, for having a fast detector, we're using a downscaled image. But for our second neural net, we can take a full resolution part to have like higher accuracy. Next, from detector, we need a good detection. From classifier, we need good classification. So we can choose models based on that, and we do not need to sacrifice classification power of the detector just because it is fast. Metrics. Here is an example. By the way, these are metrics from like real world case. As you can see on the right side, we have slightly decreased recall, but noticeably increased precision. And that's good because we don't want to spam operator. Now, let's touch a little bit on specifics of collecting the dataset for this technique. And of course, you should remember about general things like collecting balanced dataset, diverse, representative, have a good consistency in labeling, and so on. But here are a couple of things that I want to mention specifically for this task. For the detector, you need to collect data as close to inference as possible. If your inference is going to be on security cameras, you would want to collect your dataset on cameras close to that ones. For sure, you need to place it correctly to have correct angles, just how inference cameras are going to be. And of course, your objects in frame should be close to inference too. In an example of a gun, you don't need to bring a gun like to 10 centimeters in front of the camera because it is not realistic. And also, you don't want to have pictures in your dataset like the first one on this slide because it is not realistic. You are not going to get anything like that on your inference. From the classifier, you would want to create a lot of crops from your detector. It's a good idea to run your detector with a low threshold to get a lot of false positives. Then try to analyze images by yourself and select groups. Like maybe there are a lot of cell phones, so you can create a class named cell phone and put every image with cell phone there. Of course, you can find other groups like umbrellas and so on, and collect images for that classes. Finally, you can create class named other and put there all images which do not belong to any created class. With this technique, our classifier can understand if it's a gun or it's an maybe cell phone, or maybe it's just something else, just a false alert. Deployment. I will also mention it slightly. As we have said, it is important for us to have a fast solution. So we can't just train a model on PyTorch or TensorFlow and call it a day. I highly recommend converting your models to TensorRT or something similar. Basically, it's an optimization for NVIDIA GPUs, as it will make your solution faster like 2 to 5 times. And I am speaking about like real case scenario when it's faster from 2 to 5 times. Of course, NVIDIA says that it's like a lot faster, as you can see on the graph, but I'm talking from my experience. Also, second benefit is that you will need less VRAM on the inference with this kind of optimizations. So really keep an eye on that. The second thing, I recommend having a serving software, something like Triton Inference Server from NVIDIA again, or TorchServe, maybe TensorFlow Serve. It really depends on what models you use. I really would suggest to have a look to Triton Inference Server because you can put there pretty much everything, like TensorRT model, TorchScript model, PyTorch model, TensorFlow model. So yeah, pretty much everything. And basically what it is, it's a backend where you store your models and then you send requests with images for processing. That will really help you with scaling your deployed solution. Examples. Let me give you some examples of models and things that you should know. So if you're going to get a task like this one, you know where to start. As a first neural net detector, I often use YOLO family models. Maybe YOLO V5 or currently YOLO V8 is pretty good. I would recommend it. And why is it good? There are several models from nano version to extra large. It means that you can find a model size for your case, for your hardware, for your task. You can start with something like YOLO V5 Model S, small, and then just understand if you need a more like bigger model or faster model. And the second plus of YOLO models is that they convert to TensorRT really easily. And this is really important because you are basically getting your solution speed like x3, realistically saying. Okay, as our second model classifier, I often use EfficientNet. I often start with it, at least. It also has different sizes, like around 8. So again, you can choose for your task, and it's great. And yeah, that's basically it with examples. Let's just sum it up. When you need to deploy an object detection solution, which is going to be 24/7 system, and you need to increase your precision without sacrificing the speed of the solution, try using Cascade type of models. So detector, the first model, and classifier as your second model. And your second model runs on the crop of the detector only in case when your first model detector finds anything. And that's basically it.
Thank you very much, Argo. Do we have
you.
any questions coming from the audience? I don't see any. So thank you very much for your session. Thank you very much for the participation. Thank you to our audience for staying with us for the whole day. Enjoy the rest of the conference. Come early at tomorrow for the sessions that start in the morning. And of course, have a nice evening.
Thank you
Take
very
care.
much.
Bye.
Have a nice day. Bye.